In this video, we're going to look at a more realistic buck converter example. So during this video, I would encourage you to pause and try to work on your own at a few of the points to get some extra practice with designing these types of buck converters. So for this design example, we're saying that we have a nominal 12 volt input from a car battery, and we're wanting to use that 12 volt battery to charge a phone. So car power supply. And we want to use that to charge a cell phone. And so we want to charge our cell phone at a voltage of 3.6 volts. Okay, so a couple assumptions. We're going to say we're told that our power, so assume our max power drawn is 2 watts. And the power never goes below 1 watt. Okay. So a couple additional assumptions or sort of constraints. So we have this constraint, the set of constraints related to our power, but then we also know that we're told we want to stay in continuous current mode. So we never want our output current to be dropping to 0. So continuous current mode. So I out greater than 0. And we also are given the range of our V raw, our input. So our range of V raw. So for our one extreme condition, we have 9 volts. So we're told this is nominally a 12 volt battery, but maybe our battery is dying or maybe it's being loaded down with a lot of other stuff. So we have 9 volts would be the minimum voltage that we see from that battery. And then let's say on the other end, we might see some 30 volt spikes. And so this would just be from maybe a circuit in a car is not necessarily built to be well regulated and protect all the electronics from this type of short-term spike in the system. So maybe we just have a noisy circuit in there. Okay, so of course this is kind of a rhetorical question, but if we weren't watching a video on buck converter design examples and you were just given this information shown on the screen right now, you might ask yourself, what type of converter do we need? And so the answer is, of course, we need a buck converter because we're stepping down. As we're going to see in some other videos, of course, we talked about types of converters that could go up or down, but if we know we're going to go only in one direction with a particular circuit, for instance, down converting, then our buck converter is going to typically be a better choice. So if we look at this circuit here, this is sort of a modified version of the buck converter that we've seen previously. The only difference is that I've replaced a switch with this MOSFET. And so what this represents, and I'll put some specs here in a little bit, so from the Stephen textbook, one example of a MOSFET that we could use here would be an IRF 820A. And so that's an N-channel FET. And so you notice that there's also a diode in here, D2, and so that's included in this FET package, and that's just a protection diode built in to help preserve our FET in certain conditions. So and notice I also have down here on our gate of our MOSFET, we'll have some type of switch driver circuit, which is telling this our MOSFET when to turn on and off. And so that's equivalent to a switch opening and closing. So our specs for this N-channel FET, so let's say our IRF 820A specs are as follows. So we have a VDS max, so that's our drain to source voltage, so sort of across here, drain to source. And so the VDS max is going to be 200 volts. We also know that our ID max, our drain current, is equal to 2.5 amps. So we see this device is able to handle relatively large currents and voltages. We're also told that our TS on, so this is the time to get to our on state. So we're no longer assuming we have this ideal instantaneous switching. So TS on is 20 nanoseconds, and our TS off is 30 nanoseconds. And so again, all of this is information that would be available in the data sheet. And just be aware that some of this might change based on your operating frequency or your operating conditions. Okay, so one other thing, sort of one other general rule that we want to point out before we get into our analysis is related to our switching time. So a general rule is that our longest transition time should not be greater than 10% of either our on or off time, whichever one is lower. So our longest transition time, and so by transition time we're talking about this TS on and this TS off, and so we're saying this should not be greater than approximately 10% of the lesser of our total on time or total off time. And so what this essentially means is that we don't want the actual switching up and down. So we recall, so we're not going to be going straight up instantaneous. We're going to take some time to get to this state, and then we're going to take some time to come down from this state. And so what we're saying is that we want these transition times here, let me just draw a long line, these transition times here to be an insignificant portion of that. So rule of thumb, we want to keep that at least less than 10% of the smaller of our on time, which would be up here, or our off time, which would be down here. And so the reason we want to do that is keep in mind that most of our power consumption occurs during switching. So most of our power. And so of course to some extent that's going to depend on some of the other factors such as our I max, our V min, like we've seen previously, but in general, for a generalized system, we can say most of our power is consumed during our switching. Okay, so I think we have enough information now to sort of get into solving this problem. And so first of all, we could ask ourselves, what are we even trying to solve for? So based on all this information we're giving up here, the main thing that we're left to solve for is the value of our inductor L. The reason I can say that is because we're not given any information, any regulation about our ripple voltage. So for our ripple voltage, we're not really going to be too concerned about this capacitor value C then. And for our diode, we're assuming that it's just going to be blocking as the same way that we described when we introduced our buck converter. So ultimately what we're looking for is this value of our inductor L. Okay, so where are we even going to start with this? So we can actually start with our max and min powers and relate that to our voltages, and that's going to give us our max and min currents in our output load. So let's do that. So our max and min output currents, we can say our, so sort of draw a line here, we're on our new topic. So we have I max is of course going to correspond to when we have maximum power output. And we're going to say, of course, that just corresponds to what we're assuming is a constant V out because we weren't told otherwise. So our maximum power, we said it got up to 2 watts. Output is 3.6 volts. We plug that in and we see that's going to be approximately 556 milliamps. Our I min is just going to correspond to our minimum power. We still have this same V out voltage, so now we have 1 watt divided by our 3.6 volts, and we see that that is going to be approximately 278 milliamps. Okay, so the other piece of information that we have is depending on what our V raw is, we're going to have two possible duty cycles, two possible on times. So let's look at those two cases here. So let's look at our duty cycle ranges. Okay, so in general, we know that our debug is just equal to T on over T. And we also know that our debug is equal to V naught over V raw. So if we have a consistent period capital T, we can see, and a consistent output voltage V naught, we can see that as our raw input voltage is changing, we're talking about a change in our T on. So we can talk about a debug max. And so our debug max is going to correspond to when we have the minimum V raw. So that is V out divided by V raw min. And so our V out, we're saying, is constant at that 3.6 volts. And our V raw min, we said that's the case when our battery is dying, and it's down around 9 volts. So in this case, we have debug of 0.4 or 40% duty cycle. Now our minimum duty cycle, debug min, is going to correspond to when we have the maximum V raw. So these are those short voltage spikes getting up to 30 volts. So we have V raw max, so we have our output staying constant at 3.6 volts, and we have our 30 volt voltage spike in our system. So in this case, our duty cycle is 0.12, or it's on 12% of the time. Okay, so what we want to do now is we want to combine this information with our specifications for our MOSFET that's going to be acting as our switch. Particularly, we want to focus on our TS on and our TS off. All right, so what we want to do, well, before we do that, I want to make one note here. So we can note that this 0.12 is close to that limit we talked about in a previous video. We said this is close to our 10-to-1 step-down ratio. We said if you go any larger than that step-down ratio, that it's better to use multiple buck converters in series or sort of in cascade. But in this case, since it's just a short 30-volt spike, it's not a sustained voltage, we're pretty okay because we're not exceeding that 10-to-1, but we're not going to be there for very long. Okay, so now what we can say is we want to increase our frequency so we can have the small of an L value as possible. So what we're going to do is we're going to look at our longest switching time. So I want to consider our longest switching time, and that's going to be our TS off. So TS off. And what we want to do is we want to set that then equal to 10% of the smallest duty cycle time. So actually, let me change this. So we're going to set this set it equal to 10% of smallest T on. And so our smallest T on is going to correspond to this case when we have this smallest duty cycle, the smallest debug min. Okay, so what we're going to do with that then, and again, we're not worried about this too much because this is a spike, this 30 volts, so it's just happening sort of briefly. So what we can say is we have our TS off, and we know that that's equal to 30 nanoseconds from our specifications. And what we want is we want this to be equal to 10%, so 0.1 times our T on associated with this case here. So remember, our T on can be written as T debug. So I'm going to write T debug, and this is debug min, because that's going to be our smallest T on. So I'll just come up here and say that this is our T on min, essentially. So we can plug in values for that debug min, and we have, of course, 0.1 times 0.12 is our debug min, and that's multiplied by t. And so what we can do now is we can solve for that t value. So if we solve for that t value, we see that our t is equal to 2.5 microseconds. And we just invert that to get our frequency. And we can select a frequency of 400 kilohertz. So this is based on the specs of our MOSFET available. This is reasonably the highest frequency that we can choose in order to minimize the value of the inductor that we're going to need. And so, of course, smaller inductor value means a cheaper inductor in most cases. And again, notice we had to use the smaller t on time just because of that general rule we stated of keeping our switching time less than 10% of the smallest t on or t off time. Okay, so now we know our switching frequency. So as I've mentioned before, we don't have any specification for V ripple. So no specs for V ripple or for our I ripple. The only thing we're told is that we want to keep it operating in continuous mode. So let me just scroll back up here briefly. So we're told that we want to be in continuous mode. So we're not told to keep our I ripple below a certain value. We're just told to keep that I above 0. So because of that, we can determine the L right at the threshold between continuous and discontinuous modes. So as I've said before, no specs for V ripple means we're not concerned about our capacitor. So not concerned about capacitor. And for our I ripple, what this means is then we can choose determine L that corresponds to our transition point between continuous and discontinuous modes. And so what we can do from that is we can say here's the limit, and then of course we can say if we increase it or decrease it, we're going into continuous or discontinuous mode respectively. And so again, keep in mind we defined our discontinuous is when our inductor current is going to 0. So in this case, we're saying our inductor current is just reaching 0, and at that very instant, the switch closes and it starts charging up again. So let's sort of just briefly draw what this is looking like then. So let's come here. Let's draw some plots for our switch, for our raw, and for our output current. So let me just copy this. Okay, so for all of these, we're looking at things over time. So we're talking about our switch, we're talking about our I raw in the second plot, and that's going to be going between I2 and 0. So down here we have I1 is equal to 0 because we're saying it's just barely touching 0 at sort of the limit when the switch is closing again. And then finally down here we have I0. So to sort of keep this straight, what we're talking about for the different plots, I'll highlight what each plot is. So down here we'll also have I2 and I1, which is equal to 0. Okay, so for our switch waveform, and so let's say up here we have on, and down here we have off, and so of course that corresponds to closed and open. And so for our switch waveform, we have roughly a 12% duty cycle, so I'm not going to necessarily try to draw that exactly accurately, but what that would look like is we have this on for a short amount of time, and then it's off for a longer amount of time, and then it comes on again. Let's try that again, so something like this. And so note this should be a 12% duty cycle, so that's not to scale, just to kind of help us get an idea. Okay, so what's happening with our I raw then is we know that it is 0 when the switch is closed, and then at that point when our switch is open at 0. When our switch closes, it begins charging up. So it's going to charge up to a value of I2, and then when the switch opens again, it drops back down to 0. And same thing happens for this other switching instance. It begins charging up when the switch closes, and when the switch opens, it drops down to 0. And again, keep in mind, we're not talking about a physical switch. In this case, we're talking about our MOSFET, which is behaving like a switch. Okay, so now what does our output current look like? So our output current, again, we're assuming this was in steady state before, so it has been decreasing, and it decreases to where it just reaches 0, and then that switch closes and it charges up to I2. And so I've drawn this kind of poorly, but basically what we should have is this should be decreasing to where it's just reaching 0, and then that switch closes, and then it increases to I2, and then it's decreasing, and it just keeps on repeating like that. So the key thing to note is that it's just barely coming into contact with 0 at these points here. So it's not staying at 0 for any length of time. Okay, so now we can look at how we can calculate our L value based on all this information. So we know in general our delta I buck is equal to T on times V raw minus V out over L. We also know that our delta I buck is equal to I2 minus I1. And so the first of these two equations is one we had derived previously, and then the second one is what we can see just sort of looking at the graph. So remember, our delta I buck is like our ripple current. So looking at this graph, we can see it's varying between our I2 and our I1. In this case, because our I1 is 0, this is just equal to I2. Okay? So now we want to consider sort of the worst case. So our worst case we can think of is going to be when this I2 is as small as possible. And so what we're going to see is that's going to correspond to when our I min, so when we have our lowest output current. So let's say our worst case occurs for I min. So our I2 is closer to 0, which means it doesn't take as much time to decay towards 0 with the same inductor. For I min being drawn, and that occurs for our 30 volt spike, which is the 12% duty cycle. Let me write that out explicitly. Okay, and so the basic idea, again, is if this current level I2 is closer to 0, it's taking less time to get to 0 as it's decaying. So this is why we're considering this as our worst case. Okay, so our average output current we can define. So average output current. So assuming that we have a plot that looks something like this here, shown on the screen now, our average output current is going to be equal to our I min, because again we're saying that is our worst case, and we're saying that that average output current is equal to I2 divided by 2. So when I say average output current, let me come in here and draw in a different color. So we're saying we have some average value right here, and again I've not drawn this graph particularly well, but this should be sort of the average value through there. Okay. So now what we want to do is we want to kind of combine some of these equations. So we can say our I2 is equal to 2I naught. And we know that that is equal to, from our previous equation up top, T on times V raw minus V out, and all of that divided by L. Okay, so now we want to rearrange this and solve for our L. So we can say our L is equal to, and T on I'm going to replace with debug times T. And then we have our V raw minus V out. And we're dividing by 2I naught. And so remember, this 2I naught is equal to our I min. So really I could go ahead and change this for clarity to say this is 2 times I min. Okay, so now it's just a matter of plugging in our values. So our debug, remember we're talking about this worst case scenario where we have our 12% duty cycle, so the debug is 0.12. Our T is 2.5 microseconds, so I'm going to write that out 2.5 times 10 to the minus 6 seconds. V raw, again, for this worst case, we're talking about that 30 volt spike, minus our V out, which we're assuming is constant at 3.6. And then in the denominator, we have 2 times our I min, which we found what seems like ages ago now, up here from our minimum power to be 278 milliamps. So we come back down here and we say 278 times 10 to the minus 3 amps. And if we solve for that, we get that our L is approximately 14.245 microhenries. And so again, remember that this is sort of the boundary condition. This is the lower limit of our L value. If our L value gets any lower, we'll then be in our discontinuous mode. So what we can say then is if we just increase this L value, what that's going to lead to is a decrease in our delta I buck. And so, or in other words, a decrease in our output ripple current. And so what that means is we're not going to be reaching 0, so we're not going to be at risk of operating in our discontinuous mode. So that was a lot more detailed example. So hopefully all of that made sense, but please let me know if you have any questions.